In this video, we're going to look at variable acceleration. Kinematics is the study of displacement, velocity, and acceleration, and we've seen that in situations involving constant acceleration, we can apply the constant acceleration formula, and we should be familiar as well where these formula all came from. So if we have a velocity time graph, this is what we have for constant acceleration where there's a straight line. So let's say that the initial velocity is u and the final velocity is v, and it takes t seconds to reach that from an initial time of 0. So looking at the area underneath that graph, the area is a trapezium, and the area is going to be a half of u plus v times t, and the area underneath the velocity time graph gives us distance. So that's where the last formula is coming from. If we were to work out the gradient of the line, and the gradient of a velocity time graph of a straight line is the rise over the run, and the gradient works out to be acceleration, then we get A equals v minus u over t minus 0, and that's considering this as a point tv and this as a point 0u. So this is a gradient. That simplifies to A equals v minus u over t. Multiplying up by t, we get at equals v minus u, so v equals u plus at. And we've got another constant acceleration equation. To work out the other two, all we need to do is substitute v equals u plus at in for v, and that will get us our s equals ut plus a half at squared. And then the other way is to rearrange v equals u plus at for t, and that would be t equals v minus u over a. And if we substitute that in for, again to the equation up here, then that will give us our last constant acceleration equation. The unfortunate thing is that whenever we come to a situation where we've got variable acceleration, then the constant acceleration formula are useless. So we have to use calculus then if we've got non-uniform or variable acceleration. Graphically, that would look like a curve in our velocity time graph. So if we consider the following relationships, we should know that velocity is the rate of change of displacement. Now, rate of change is the differential of displacement with respect to time. So then what we can say is that velocity is equal to ds by dt, or sometimes referred to as s dot. So if we differentiate displacement with respect to time, we get our velocity. Similarly, we should know that acceleration is the rate of change of velocity, so it's the gradient of a velocity time, and gradient is the rate of change. So then the rate of change with velocity is dv by dt, or v dot, but what we've got then is that a is also the differential of ds by dt with respect to time. So because we're differentiating velocity with respect to time, we know that velocity is ds by dt, then we could say that it's d2s by dt squared, or in fact s double dot, and that's what we can see here. So what we have then is if we want to get from displacement to velocity, we differentiate, and from velocity to acceleration, we differentiate again. Then if we're differentiating one way, we can integrate back the way. So if we want to get from acceleration to velocity, we'll integrate with respect to t, and to get from displacement from velocity, we'll integrate again with respect to t. And each time we integrate, we'll have to introduce a constant of integration. If we were to integrate a with respect to t, we would get some function t plus c, and if we were to integrate that function of time with respect to t, we would get some higher function of t plus a different constant d. So we couldn't reuse c because that way we could get confused with the previous one, so it'll be a different constant of integration. So in this example, we've got a body that moves in a straight line such that A is equal to 6t. Initially, the velocity of the body is 2. Find A when t equals 5. So we've got A equals 6t. When t equals 5, A is going to be 6 times 5, which is 30 meters per squared second. Part B, we want to find the velocity. Now, velocity is the integral of A with respect to time. So that's going to be the integral of 6t dt, which is 3t squared plus c. So velocity is 3t squared plus c. Now, what we know initially, the velocity is 2 meters seconds, and initially means when time is 0. So when t equals 0, we know that v equals 2. So then if we substitute that in, we get 2 equals 3 upon 0 squared plus c. So that means that 2 is equal to c. So our velocity equation is v equals 3t squared plus 2. Now we want to find v when t equals 3. So when t equals 3, we have v equals 3 times 3 squared plus 2, which is 3 times 9 plus 2, which is 29 meters per second. Our second example then, a body moves in a straight line such that v is 2t squared minus 11t plus 14 initially. So again, we can see that means that time equals 0. The displacement of a body from some fixed point O is 50 meters. Find the initial velocity. Initial velocity then, so t equals 0. V equals 2 times 0 squared minus 11 times 0 plus 14, which is 14 meters per second. Part 2, we have the value of t when body is at rest. And at rest means velocity is 0. So we're going to have 2t squared minus 11t plus 14 equals 0. We can try and solve this using sum and product. Sum is minus 11, product is 28, and the numbers there are going to be minus 7 and minus 4. The two brackets will be 2t and a minus 2, t and minus 7. So that means that 2t minus 7 is 0, or t minus 2 is 0. So t equals 3.5, or t equals 2. Part 3, we've got the displacement, and the acceleration. And the acceleration is dv by dt, which is going to be the differential of 2t squared minus 11t plus 14 with respect to time, which is 4t minus 11. When t equals 4, A is going to be 4 times 4 minus 11, which is 16 minus 11, or 5 meters per second squared. Part 4, we've got the displacement, and the displacement is the integral of v with respect to time, which is the integral of 2t squared minus 11t plus 14 dt. So that's going to be 2/3 t cubed minus 11t squared over 2 plus 14t plus c. Now we're told initially, so that's whenever t equals 0, s equals 50. And whenever we put t equals 0 into the equation, the 2/3 t cubed will be 0, minus 11t squared over 2 will be 0, 14t will be 0. So what we're left with is c, so that means that c is going to equal 50. So s equals 2/3 t cubed minus 11 over 2 t squared plus 14t plus 50. When t equals 6, s then is equal to 80 meters. Example, a particle moves in straight lines so that at time t its velocity v is given by minus 10 plus 12t minus 2t squared. At times t equals 2, the particle is at A. Find the times when the particle is at rest. So at rest, remember, v equals 0. So we're going to have minus 2t squared plus 12t minus 10 equals 0. We could divide through by minus 2 and get t squared minus 6t plus 5 equals 0. Factorising, we get t minus 5, t minus 1 equals 0. So t is equal to 5 or 1. So then the times when the particle is at rest is 5 seconds and 1 second. Part 2, an expression for displacement. So s is the integral of v dt, which is the integral. Now, we divided v by minus 2 whenever we were solving it equal to 0. We can't do that here. We just have to integrate our formula for v. So it's going to be the integral of minus 10 plus 12t minus 2t squared dt. So s is going to equal minus 10t plus 6t squared minus 2/3 t cubed plus c. We're told when t equals 2, the particle is at point A. And because we're asked for the expression from A, that means when t equals 0, s equals 0. And if we were to put those in, we would get 0 equals minus 10 times 0 plus 6 times 0 squared minus 2/3 times 0 cubed. So we'd get 0 plus 0 plus c. So that means that c must also equal 0. So s equals minus 10t plus 6t squared minus 2/3 t cubed. To find the distance travelled by the particle in the first 6 seconds of motion, what I want to first consider is the velocity time graph. So we're doing v equals minus 10 plus 12t minus 2t squared, and we know that at t equals 1 and t equals 5, the velocity is 0. So that means with it being a negative quadratic graph, the velocity time graph is going to look something like this. So at t equals 1 and t equals 5, we can see that the velocity changes from a negative velocity to a positive and from a positive to a negative. And what that really means is that it's changing direction. Now, there are a couple of different ways that we can work out the the distance travelled. One way would be to integrate this velocity time graph, because the area under a velocity time graph is distance. Now we'd have to do it in 3 different parts. So 1, 2, and then because it's 6 seconds, we'd have this third part. Another one is to consider where the particle is at certain times. So at times t equals 0, at times t equals 1, at t equals 5 and t equals 6. And then that way we could try and figure out its path, knowing that when t equals 1 and 5, it's changing direction, so it'll be at the furthest point away from where it was previously. But I say considering it in terms of area is easier. So if we look for area 1, that's going to be the integral of v dt between 1 and 0. Now we've already worked out the integral of v to be minus 10t plus 6t squared minus 2/3 t cubed. So we need to evaluate that between 1 and 0. And when we do that, we get minus 4 and 2/3. For the second part, if we integrated this time between 5 and 1 for v dt, well, that's going to be minus 10t plus 6t squared minus 2/3 t cubed between 5 and 1. So that's going to equal 16 and 2/3 minus 4 and 2/3, which gives us 21 and 1/3. The last one then we need to do is between 6 and 5. So we're going to integrate v between 6 and 5, and it's minus 10t plus 6t squared minus 2/3 t cubed between 6 and 5. So that's 12 minus 16 2/3, which is minus 4 2/3. So what we've got are three different values for distance. We've got two negative ones, so whenever we're trying to find the distance travelled, we need to change those as positive. So then the total distance is 4 2/3 plus 21 1/3 plus 4 2/3, which is 30 2/3 meters. Example, a particle moves in a straight line so that at times t seconds, which is between 0 and 4, the velocity is 1.5 t squared plus 12. Find the acceleration. So acceleration is the rate of change of velocity. So that's dv by dt, which is going to be 3t. When t equals 2, a is going to be 3 times 2, so that's going to be 6 meters per squared second. At time t equals 1, the particle is at A, whose displacement from a fixed point O is 10 meters. So what's that saying is when t equals 1, s equals 10. So find an expression for the displacement. Well, s is the integral of v dt, which is the integral of 1.5 t squared plus 12 dt, which is 0.5 t cubed plus 12t plus c. We've got from the sentence before part 2 that when t equals 1, s equals 10. So we're going to have 10 equals 0.5 times 1 cubed plus 12 times 1 plus c, which means c equals minus 2.5. So s equals 0.5 t cubed plus 12t minus 2.5. Part 3, when t is bigger than 4, the acceleration is minus 12. So that means after 4 seconds, we're moving into a constant acceleration equation. So we could use our Suvat equations. What we need to do then to work out when the particle comes to rest is to find the velocity when t equals 4. So to do that, we'll substitute that into the equation. So v is going to equal 1.5 times 4 squared plus 12, which is 36 meters per second. So now if we consider our Suvat information, we don't care about the displacement. Our initial velocity is 36. When it comes to rest, the final velocity will be 0. The acceleration is minus 12, and the time is what we're looking for. So if we use v equals u plus at, we have 0 equals 36 plus minus 12t. So 12t is 36. So t is 3. So what that tells us is that it takes 3 seconds to come to rest. But we started at t equals 4. Therefore, it takes 7 seconds to come to rest. And that's from the 4 and the 3. So in part 4 we're asked to find the total distance. Now if we consider the last 3 seconds first of all, because it's constant acceleration and we've just figured out some of the information, we can do that. So we're trying to find the distance, so we'll let s equal question mark. The initial velocity was 36, final velocity is 0, the acceleration is minus 12, and the time taken was 3 seconds. So we could really use any of our Suvat equations. So let's use s equals a half of u plus v times t. So that's going to be a half of 36 plus 0 times 3, which is 54 meters. So what we know in the last 3 seconds, it travels 54 meters. Now we need to figure out the first 4 seconds. And what we need to consider is, does it come to rest in that time? So we've got 1.5, our velocity equals 1.5 t squared plus 12. And we want to see if that equals 0. Now, what we've got is 1.5 t squared equals minus 12. T squared is going to equal minus 8, and we can't take the square root of that. So that means the particle doesn't come to rest. So to work out the distance, we're going to integrate v between 4 and 0. So we already know the integral of v is a half, or 0.5 t cubed plus 12t minus 2.5. So we can evaluate that between 4 and 0. And we get 77.5 minus 2.5. And that works out to be 80 meters. Therefore, the total travelled is 80 plus 54, which is 134 meters.